there any questions? Did you guys see the video I posted on Canvas regarding the lab notebook?
I didn't see the video. I just saw a post about it. It looks like I think it was kind of like similar to the syllabus. Yeah, I was expecting a discussion, yeah.
Let me check that here. I posted in the announcements, but it didn't work. In the discussions?
Yeah.
Is there, okay, there should have been one more.
Yeah, that's just a key.
Something's wrong with. All right, I'll post it today then. For some reason, the link of this didn't post this. That's for some notebook prep. So you'll have to prepare a procedure in your notebook for tomorrow's lab. That's going to be a quiz. So take a look at the link. There's a link and Zoom video. Canvas is not working right now. We skip that. The video abruptly ends. It was supposed to go on longer, but I hit the wrong button. So to resume the video and then pause it. So unfortunately, it's not there. But I'll talk about the final step in the lab. You know, we're gonna divide the lab into 2 days. So we're just gonna do day 1. All right. Okay, where did we leave off last time? Okay. How about last week on Wednesday? Where did we leave off? Did we finish the KPKC calculation? KEQ? Okay.
We finished off with the exercise.
7A.
Yeah, 7A.
Okay, 7A.
K equals KP over RT delta.
Or did we actually finish that calculation, or we haven't finished that calculation? We finished it. Okay, that's good, because the book is not launching either. I can't get Canvas to launch in the book. To launch for some reason. I'm not sure why this is not working. So that's one way for determining K. What that means is that we don't have to measure both. For example, we don't have to measure the concentrations and we don't have to measure the pressures because the concentration and the pressures are related. So if we measure the concentrations, we can calculate the pressures. If we measure the pressures, we can calculate the concentrations. In other words, we have the relationship, KT is equal to KC, or T, and delta N again. And so that saves us some work, experimental work, because, measuring these concentrations isn't always so easy. But are there other ways to determine K? Well, experimental, and then we have this, but there are more methods to calculate K, and these are based on Hess's law. This is technically Hess's law deals with energy. Here we're dealing with equilibrium constants. So there are some differences between Hess's law for equilibrium constants, which are K, versus delta H's, which are energy. And so looking at Hess's law type applications, one is to reverse the equation. And so we'll take the reverse equation. That is, if we go GG plus HH plus dot dot dot, goes to A plus B plus dot dot dot. What we did is we flipped it. The reactants are now the products, and the products are now the reactants. I'm sorry?
Next would change that.
This one?
Yeah, no.
GG, lower upper, HH, lower upper.
Thanks.
Okay. And so we flipped it. Well, that means we're going to flip the numerator and the denominator. So when we're looking at K for the reverse, K for the reverse reaction is just equal to 1 over K for the forward reaction. And so this means we don't have to do any experimental measurements. Now, if we notice that the reaction is just the reverse of one we already know, then we can calculate it pretty easily. The other is that we change the coefficient. And so let's say we multiply by n. N or x or whatever you want to say. So we have n times GAA. We'll go with the forward this time. BB plus dot 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 goes to GG plus HH plus dot dot dot. So let's say we multiply by 2. We double the equation. Or we multiply by 1/2. We cut the equation in half. Then K for the n times is just equal to K original raised to the nth power. And so if we know what K is, and we're looking at the K value for some fraction of it or some multiple of it, we can calculate it rather than have to do this. Okay. So the other one is if we sum equations to get the net equation. This is the proper Hess's law. Hess's law, you take equation 1 plus equation 2, you get the net equation. You add up the delta H's. So you add up delta H1 plus delta H2, that's giving you delta H of the net. And so the same thing that we do here is we take equation 1 plus equation 2 plus however many equations we're combining. This gives us the net equation. Net equation. Now equation 1 is going to have a K value, K sub 1. Equation 2 is going to have a K value, K sub 2. And so the K for the net equation is just equal to the product of the K's. So it's going to be K1 times K2 times dot, dot, dot. And so rather than adding, we multiply. And so that's another major difference. And so this is not technically Hess's law as you've seen it before. It's a little bit different. But what this means is we don't have to do an experiment for every single K value. If we have a library of K values, then we can figure out, a number of equations just by adding or multiplying or reversing, and then we can calculate the K value from data in the tables rather than from equilibrium concentrations or equilibrium pressures. Okay, I was going to do some examples of this from the book, but it's still not loading. Oh, did it just load? It's still not loading. So what we're going to do is I'm going to skip doing any examples of this. You can see it in the book, but I think it's fairly straightforward. What we're going to do is we're going to use K for stoichiometry calculations. And so this is an application of K. So using K for stoichiometry. So let's take a look at some data. Okay, here's some data here. What kind of reactions are these here? Or on the right? The reactions? Like Ag plus 2 ammonia yields this. What are these reactions here? What are those? Metathesis, redox, acid base. Metathesis, redox, or acid base. Metathesis is a favorable ion combination, but when you look at ammonium, is ammonia an ion? No, so it's not metathesis technically. It is it redox? No, it's not redox. It's acid base, but what kind of acid base is it? Lewis. So you don't have much experience with Lewis acid bases. How are we going to get it? Well, Lewis acid bases are more complicated than Bronsted. And so what we're going to do is we're just going to take some observations. So for example, how do you know? Why is it 2 ammonia? Why isn't it 4 ammonias or 6 ammonias? Why is it 2 ammonias?
Because
In other words, can you come up with a hypothesis telling me how many ammonias will react with each metal? Can you just whip up a hypothesis right now? No. And this is like the science in science, no, that's too hard. So instead what we do is we take a look at the observations. What happens? These are the observations that we see. I don't know why it's 2, but that's what's observed, 2 ammonias. And so one of the ways to get more familiar with these Lewis acid base reactions that form metal complexes is just to look at what forms. And so we have a table like this. There's a table like this very similar in your book. Maybe it's a little bit longer. But these are some common metal complexes that we see. So let's take a look at and just name these first. In fact, we're going to be seeing metal complexes. And so what I'm going to do is for the nomenclature for these we'll hold off on the test or the quiz for the nomenclature until later when you get more comfortable with these. The same thing with the reactions. We're going to be looking at reactions throughout the semester. So probably nearer towards the end of the semester, we'll have a little test or quiz on those. And so the first test is going to be with chapter 15. The chapter 15 test, I'll finish chapter 15 this week, and probably next week we'll have a test on it. So let's name this one here. Diamine. Silver monoxide. Yeah, that's good. And this is a linear. Okay, let's go to this one here. What's this one? Dicyano, or our book, the new name for this, cyanido, but cyano is probably more common. You'll see. Dicyano, argentate, 1. Does the 1 come from the -1 charge here? No, the 1 comes from where? The positive charge on the metal. So cyanide is -1. We have two of those, -2 plus 1. Plus 1 for that one. So let's go on to this one. This is do you recognize the sign here? It's oxalate C2O4.
Yeah. Thiosulfate.
Thiosulfate, yeah. This is thiosulfate. Is thiosulfate a monodentate or a bidentate ligand? Monodentate. This is one of the examples we looked at in lab. Thiosulfate is monodentate, or I think it was lab. And so this is, what's this called? Okay, we have to add the O on the end. So this would be diethiosulfato argentate 1. Yeah, because thiosulfate's a -2. It's 2 times -2 -4. -4 plus 1 gives us -3. So it's got to be Roman numeral 1. Now, is this a linear complex? What's the coordination number of this? Or silver? What's the coordination number on silver? 2. 2 is correct. So now we see a collection of silvers. What do you notice? What's the pattern with silver? It likes to form. Oh, well, it's not bidentate. This is monodentate. 2 monodentates. It likes to form, well, a coordination number of 2, which means that they're going to be linear complexes. So silver likes to form linear complexes with coordination number 2. That's just based on observation. Now, if you see observations where it's forming coordination number 4, coordination number 6, then we have to see what's going on. Okay, that's silver. Let's look at what's next here. How would you name this one? Tetrabromo. Cadmium or cadmiumate? Cadmiumate. And now cadmiumate doesn't sound so fancy like argentate or plumate or stanate, but we'll have to live with it. And so this would be tetrabromo or tetrabromido, if calling it now. I'll just call it tetrabromo. Tetrabromo, cadmiumate. And the charge on the metal is +2. Yeah. Each bromide's -1, so -1 times 4 plus 2, and it's -2. That's good. Now, is this one tetrahedral or is it square planar? It turns out that this one is tetrahedral. Just from observation. I don't, predict it. How would you predict it? One of the things about tetrahedral complexes is usually we have filled shells and filled subshells in the metal. And so cadmium 2+, if we go to cadmium on the periodic table, +1 plus 2 gives it an electron configuration of argon 3d10. Argon's filled core and 3d10's filled subshell. So typically we'll have that. Or aluminum 3+. Aluminum 3+ has no d electrons. Aluminum 3+ is the neon configuration that's filled shell. That turns out to be tetrahedral as well. When we have a partially filled, like for example, nickel 2+. Nickel 2+ has an electron configuration of argon 3d8, then that's square planar. Same thing with platinum 2+. And so there's some patterns in there that we can find, but for right now, we're not going to worry about it. But eventually, this is the first step. The first step is just to look, at the data, see if there are any patterns there, and then go from there. And then much later on, maybe we can come up with a hypothesis. Why tetrahedral? Why square planar? Why coordination number 2? Why coordination number 6? But that's going to come from some hypothesis, which will eventually lead to some kind of theory on the complexes. And, anyway, going on, what is the name of this? Tetrahydroxido. Chromate. All right, chromate 3 is correct. Roman numeral. Hydroxide -1 times 4 is -4. -4 plus 3 will give us a net charge of -1. So this is Roman numeral 3. Is that tetrahedral or square plane? I don't know. Just look it up. We'll look it up initially and then try to figure it out from there. How about this one? This is not as common of a ligand, but just try to figure out what it is on this table. It looks like ammonia is pretty common, and what else looks pretty cyanide. Those are two excellent ligands, especially cyanide. It's very good. Ligand would be the Lewis base. All right, what is this one called here? Well, this one, there's an OCN. OCN is called cyanate. An SCN, where you replace an oxygen with a sulfur, is called, when we have an S replacing an oxygen, we call it thio. Yeah, so this one's called thiocyanate, the anion. As a ligand, we drop the E and add no, and we call this, what? Thiocyanato. Thiocyanato. And so how would we name this complex here? Yeah. Thiocyanate's -1. We have 4 of those, so this is going to be +2. Okay. Let's move on here. Tetramine. Copper 2. Yeah, we saw this one in lab. This is the deep blue ion, deep blue colored ion, deep blue colored solution. We also saw this one. This is colorless. The diamine silver is colorless. This one has a very intense blue color to it. How about this next one here? This is hexamine nickel 2, which also has a color to it. As do these. This one is called ferrate. Now cyanide's -1. So -1 times 6 is -6 plus what with this? Yeah, it's ferrate 2, Roman numeral 2. And then finally this one here. Yeah, hexacyanoferrate 3. Well, these are the reactions. These are called formation reactions. It's formation of the metal complex here. And so what they do with the K's is they put a little F there, just meaning it's formation of the complex here from the metal and the ligands. Okay, this is a different than the delta H formation. Delta H formation is from the elements in their standard state. This is from the Lewis acid and the Lewis bases. And so it's a different kind of formation reaction. And the numbers will be different. If you look at these reactions here, the K's, look at the K, you look at the general K's, are those big, small, or just kind of in the middle? These are big, yeah, big. Look at 10 to the 42. That's gigantic. The smallest one is 10 to the third. 10 to the third is still 1,000, 1,000 to 1. And so all these are big, meaning these are all excellent reactions, excellent Lewis acid base reactions that we see here. Even, even bromido or bromo is not that great of a ligand, but still it's pretty good, 5,000 in this case. And you would, if you were thinking of Bronsted base, bromide is an awful Bronsted base, neutral. But bromide in this case is a pretty decent Lewis base here because that's still highly favored reaction. And so all these are heavily product favored, meaning that these are excellent Lewis acid base reactions.
So there would never be a time you would ask us like, oh, is this an exothermic or endothermic reaction for those types of, okay, that's one
That brings up a good point. There is a time where I will ask you, because there's one more method of determining K. This is later on. So let me just add it over here because this is in the thermodynamics chapter. When we get to thermodynamics part 2, we can calculate K. Calculate K from thermodynamic data. And in the thermodynamic data, you're going to have things like delta H, and delta H could be positive or negative. And so from that data, you might be able to determine what the delta H is. You might be given a delta H. But we calculate K from thermodynamic data. This is the most powerful method. Of determining K. The Hess's law stuff is very limited. The KC and KT is very limited, but this is very powerful. In other words, you can calculate the K value for a heck of a lot of reactions if we know the delta H, if we know the delta H and one other thing, if we know the delta S. Delta S is entropy. And so, if we have the delta H and the delta S value for these kinds of things, or the delta G value, we can go ahead and calculate the K value here pretty easily. And this is going to be discussed later. And that's my preferred method of determining K because it's simple. We have thermodynamic data tables in the book, so we can look up stuff. When we look at the thermodynamic data tables in the book, it's the delta H is going to be given for you, so you don't really have to predict whether it's exothermic or endothermic. Just read it off the table. So once we have a K value, then and K values are very useful. So other people have done the experiments, or other people have done the calculations and filed the Ks in the table, like here. Now, who did this? Well, somebody did that. It could be quite a bit of work. But what are we going to do with it? What we're going to do with it is we're going to use the K value to do stoichiometry. This is Chem1B stoichiometry. So let's take a look at this silver reaction up here to form the diamine silver. So examples will be Ag plus 2 ammonia. Ammonia is a good ligand, good Lewis base. Silver likes to form 2 coordinate complexes. So we have 2 ammonias. Find that. And this is a highly favorable reaction. 1.7 times 10 to the 7 would be 17 million to 1. And this would be K. And you say K. This is a KC, by the way. KFs are KC values. Okay. So,
Wait, say KC and KF are the same.
yeah. For these equations, it's the same. So for this one, what we're going to do is we're just going to take some silver ion here. let's say I have 0.100 molar Ag plus. And so I'll give you like silver nitrate or something, just some silver ion source, silver acetate, silver nitrate, silver chlorate, or something like that. Okay. And to this, I'm going to add some ammonia, H3. I'm going to add enough ammonia here to make it 3.000 molar ammonia. And so initially, I'm going to take some silver ion, so I'll put I here, at 0.100 molar, and then I'm adding enough ammonia to make the whole thing 3.000 molar in ammonia. And then what's going to happen is this is a very favorable reaction. The ammonia is going to attack the silver to form the diamine silver. We saw this reaction occur in lab, when we added ammonia. I need to talk about those reactions that we saw in lab in depth. But initially, we just mix this together and we assume nothing's happened yet. And then what's going to happen is the ammonia attacks the silver. Well, how much? Is it going to attack all of it? Well, it's not going to attack all of it because it's not infinite. If K were infinite, then it'd attack all of it and we'd have 100% reaction. So it's going to attack some of it. I say a lot of it because that K is pretty big. And so we don't know how much, so we're just going to call it X. We're just going to lose some amount, X molar. Now, based on stoichiometry, if I lose one silver, how many ammonias do I lose?
One. About two.
Yeah, it's a 1 to 2 ratio, so this is going to be minus 2x molar here. And it's a 1 to 1, 2 to 1. And so I'm going to gain plus x molar here. So by the time this reaction has finished, I'm going to have 0.100 minus x molar. I'm going to lose some fraction of it. I'm going to have 3.000 minus 2x molar, and then x molar here. Well, how much reaction am I going to have? Well, I can figure out how much reaction I'm going to have because, well, I have one unknown here. I need the equation to get that. And so this equation, actually, give it to me. So what I'm going to have is I'm going to have the concentration of the diamine silver here, and then divided by the concentration of silver over here, and then the concentration of the ammonia. The concentration of ammonia has to be what? Yeah. Okay, and then I want to label a couple of things. When we talk about complex formation, these formation reactions, we typically call this the free silver. So this is free silver versus this is complex silver. And so if we add up the free silver and the complex silver at equilibrium, that gives us the total silver, or actually anywhere. So the total silver is the free plus the complex. And so in the stoichiometry calculation, we want to figure out how much free silver is left and how much complex silver we have. The way we can do that is we'll just substitute these equilibrium concentrations into the equilibrium K expression. All these are equilibrium here, not initial. So we'll go ahead and do that calculation here. This is going to equal X divided by 0.100 minus X divided by 3.000 minus 2x quantity squared. Okay, so now all we have to do is solve for x. And so why don't you go ahead and solve this for x? 2. Okay. So you got x is equal to
8.8846 times 10 to the negative 2.
Okay. Okay, we can take a look at this one in just a minute. So one thing is, the algebra is pretty hard, right? Algebra, and so, and then, this is not a class for algebra, this is a class for chemistry. And so what should we do in a situation like this? One thing we can do is, if we have a calculator, you're limited in what types of calculators you can use for this class. But if you have, let's say, a lot of calculators that are acceptable for standardized tests will have a polynomial equation solver, like the FX115. It can solve quadratics and it can solve cubic equations. And so if we could get this into cubic form, ax cubed plus bx squared plus cx plus d, then we could just use our calculator and plug that in. Did anybody do that? Is that what you did? You got it in cubic form and then you plugged it in? Okay. And so you get it in this form, and getting in this form, that's a lot of work, for sure. But if you don't know if this is right or not, how can we check it? Well, usually we just check the answer in the back of the book, right? But you can't do that in this case because I made up the problem and it's not in the book. And I don't have the answer to this. And so how do we check our answer? Okay, this is the way we check our answer. So if we get this, then we can calculate the equilibrium concentrations. And so we'll go over here and we'll calculate the equilibrium concentrations. So the first one is 0.100 minus, okay, I'm going to just convert this into decimal form. So this is going to be 0.088. And I'm going to carry extra digits. We're only allowed 2 6/8, but I'm going to carry extra to make sure we don't have any round off error. So we'll have this. And so what does this come out to here? This is going to come out to 0.0154. Is that right? Okay, then we go over here. This is going to be equal to 3.000 minus 2 times that. And so we'll have to double this. So doubling that, I'll just punch it in the calculator because I don't want to do it just yet. Actually, somebody can just do this in the calculator. What do you come out with here?
For the answer, I got 2.977692.
2.967
Yeah. 2.977
692. Thank you. Okay, I'm going to ignore sig figs right now. We'll just fix it later. And then x, this is easy. This will just be 8.8846 times 10 to the minus 2 more. All right, these are the equilibrium concentrations. This is,
I think I messed up.
okay. All right.
I used the wrong list.
Okay. Let me erase this then.
I got 2.822308.
2.8
22.
308. Okay, thanks. I'm carrying extra digits because this is how we're going to check our answer. And we want to carry extra digits to check our answer because we don't want round off error. If we have round off error, then it's going to be confusing if we did the calculation correctly or not. And so the question is, how do you check your answer? to make sure it's correct. And the answer is, how do we check our answer? We plug it back into the K equation and see. We know what K is supposed to be. K is supposed to be 1.7 times 10 to the 7th. Are we going to get that by using these equilibrium concentrations? And so what we're going to do is we're just going to plug it back into the equation. This is going to be 8.8846 times 10 to the minus 2 divided by, okay, it's going to be the silver ion concentration, 0.011154, divided by 2.822308 squared. Okay, and let's calculate this number and see what it comes out to.
I think the number is not in the center. If you look at the denominator, there's a 2.8 square. So that's like a big number, like 4 or 5-ish.
Yeah.
And then the numerator is super small.
Yeah.
That doesn't even be
Okay, well, let's go ahead and calculate it regardless and then see what it comes out to see how far off we are. 8.8846 times 10 to the minus 2 divided by 0.011154 divided by 2.822308 square. Yeah. So I end up getting 0.9959999637 ... Okay. What is it supposed to be? Well, it's supposed to be 1.7 times 10 to the 7th. So that's off, unfortunately.
I got that.
Okay, so the percent error is, this means,
Well, the X I got 1.7 times 10 to the 7th.
so this tells us the answer is wrong. Right? X must be wrong. X must be wrong. Okay, again, the reason I carry so many extra digits is because rounding, round off error will make it wrong as well. We'll make the value off for 1.7. And so we want to eliminate that as a possibility. And so we tried again. We tried to solve it again. Maybe there's simple, addition or subtraction mistake. But nonetheless, this is going to take too much time. Even if you have a cubic equation solver on your calculator, getting in the cubic form takes a lot of time and is easy to make mistakes because you got to multiply this and you're going to multiply it all out. And so it's very easy to make mistakes. And so this is the reason why, a lot of people don't like this. A lot of people will just say, it's math, just solve the math, right? But this is the reason why we're going to do some tricks to make the math easier. Do you want to learn some tricks to make the math easier? Okay, then let's talk about tricks to make the math easier. And so we're going to start this problem over again. So we're back here at the starting point, and the first trick is this. We want the initial conditions to be as close to the equilibrium conditions as possible. And so if we look at it, where should most of the atoms be? Should most of the atoms be on the left side, or should most of the atoms be on the right side? In other words, should we have mostly product, or should we have mostly reactant by the end of this reaction? Mostly product. Why? Because K is so large, K is so large, this is heavily favored to product. And so what we have here is we have a deep and steep downhill. Right. All right, so this is what we're going to do. We're going to, right now, all the atoms are at the top of the cliff, and they're going to fall off the cliff. We're going to just push all the atoms off the cliff, so that all the atoms end up at the bottom. And then we're going to see that once all the atoms end up at the bottom, we're going to see how many atoms can make it back to the top. But unfortunately, we can't push all the atoms over because there is a limiting reagent and an excess reagent. What is the limiting reagent and the excess reagent here? So, ammonia, well, if we have 3 molar ammonia, that can react with 1.5 molar silver. It's a 2-to-1 ratio. So the limiting reagent is actually the silver, because if we have 0.100 molar silver, in order to react all of this, we need 0.200 molar ammonia. Do we have 0.200? We have much more than 0.200, and so this is in heavy excess. One of the reasons this is in heavy excess is Le Chatelet has pushed it to the right. You know, that can help that can help minimize the amount of free silver or maximize the amount of complex silver here.
I'm confused because I thought when you explained that last time, I remember there was an example of there was a 1-to-2 ratio, and you said that the element with the element that was multiplied by 2 was the limiting reagent because we needed 2 of those.
Well, it depends on the initial. The other one, it depended on the initial, so we didn't have enough in that case. So in this case, yeah, we do need twice as much ammonia, but we have more than twice as much ammonia. You know, we have 10 times or 30 times as much ammonia, and we don't need that much. And so we're going to have a lot of unreacted. And so this is called reset. We're going to reset the initial. We know products are heavily favored, so we're going to reset the atoms to the products. Now, if the reactants were heavily favored, we wouldn't reset. We just leave it as is. And so what we want to do is we want to reset it to the side that's favored. Or if it was already all product, no reactants, then we don't need to reset it. And so products heavily favored here. When we reset it, we're going to push all the atoms to the product side and then see how many can make it back up to the reactant side. And so what we're going to do is do the reset here. And the reset is going to be minus y molar minus 2y molar plus y molar. Now, we're just going to do this based on the limiting reagent. So we're going to have 100% forward reaction. That means we're going to lose all the free silver. So this is going to be minus 0.100 molar. And so all the silver is going to be complex. And this is going to be minus 0.200 molar, meaning twice as much. And this is going to be plus 0.100 molar. And so we're going to complex all the silver and then see how much can make it back up the hill to become free. You know, but how much do you think can make it back up the hill to become free? So we complex all the silvers down here. How much do you think can make it back up the hill to be free? Not much, because of this. You know, this is, you know, 17 million to 1. Okay, so that gives us our new initial condition, which would be the reset initial condition. And so the new initial conditions are going to be 0 molar. All of my silver has been complex, but that didn't use up all the ammonia. I'm still going to have quite a bit of leftover ammonia. It's going to be 2.800 molar ammonia. You know, I can't push those to product because there's no free ammonia in the product, only complex ammonia. And then over here, I'm going to end up with 0.100 molar ammonia. Okay, now this is more like the equilibrium. Oh, this is just 0.100 minus 0.100 here. It's the limiting reagent. The limiting reagent is going to be completely consumed in this. So what we're doing is we're assuming 100% forward reaction.
And then how to get the value from yeah.
How did I get this value here?
Well, no, from the bottom.
This one?
Yeah.
Oh, okay. If I use up all 0.100 silver, how much ammonia did I use up? Stoichiometry, just basic stoichiometry, nothing fancy. But let's say if I have 0.1 moles of silver, how many moles of ammonia do I need? Double it. And so if I use 0.1 moles of ammonia, silver, I need 0.2 moles of ammonia. Does that make sense? And so I'm doing 0.100, I need 0.200. How much do I have? I have way more. This is excess. So out of this 3 molar, I'm only using 0.2, which is going to leave me with 2.8 molar excess left over. And then this is how much product I have. This is as far to the right as it can go because I ran out of silver. I can't push it farther. In order to get more ammonia to react, I need more silver, but the silver has already gone down to 0. So there's nothing more. Okay, so essentially I pushed all the atoms that I could down the hill to the bottom. And then I'm going to see, what fraction can make it back up the hill. And that fraction is going to be quite small. And so the fraction that makes it back up the hill will be like this. And so, in other words, the complex is going to break apart. Well, how much? A very small amount, which I'm going to call minus x. So this is going to be minus x molar here. That means for every one of these that breaks apart, I form one of these. So this will be plus x. And I'm going to form 2 of these. This will be plus 2x molar. And so in other words, I'm going to try to go back up the hill, break up the complex. I'm going to form 1 silver and 2 ammonias for every, but I don't know how much. And so I'm going to call it x. It's probably a very small amount because this is heavily product favored. Does this make sense?
Right.
All right, so when we do more examples, then at equilibrium it's going to be x molar, 2.800 plus 2x molar, and 0.100 minus x molar. So in other words, rather than approaching the equilibrium from the left to the right, I'm going to go from right to left. So rather than going downhill, if I go downhill, I'm going to have a huge rush of atoms. In other words, there's going to be a significant downhill. Everybody's going to be falling off the cliff. If I go back uphill, it's very few that will do that. And so what's this going to do to the math? Well, let's take a look at the math here. And so now I'm going to have these. So I'm going to have 0.100 minus x on the top divided by x and then 2.800 plus 2x. Squared. So does that look easier or about the same? Maybe a little bit easier, yeah. So what we can do is we could get this into cubic form, ax cubed plus bx squared, etc. But still, that's going to be a tremendous amount of time and work. But there's something else that we can do. And the something else is this. If we go forward, we expect a lot of reaction because the products are so heavily favored. If we go reverse, we expect very little reaction. In fact, we expect what we call a negligible amount of reaction. And so, in other words, here, if I start off with 0.100, what's the population that I'm going to lose? The population that I'm going to lose that can make it up that big hill are just that very, very tiny population of high energy complexes that can make it back up, right? And so in other words, here, when I look at the change here, x, it's going to be very small. Versus the change in the forward direction, the change in forward direction should be quite large, like in the last setup we had. Okay, so what this is going to do is this. If the change is negligible, now negligible means different things. So let me put that in quotation marks and a little asterisk here. If the change is negligible, then we can make the following assumptions. Then 0.100 minus x is, it's such a small population that can make it up that hill. We're going to just say it's going to be close to nothing. And so 0.100 minus x is going to just be about 0.100 because maybe 1 out of a billion, 1 out of a trillion make it up. And then 2.800 plus 2x, even though this is double 2x, is still going to be about 2.800. And then the final one is 0 plus x. Well, 0 plus x is just x. So 0 plus x is just equal to x, which is not equal to 0. And so x just stays the same. This is called the simplifying assumption. Simplifying assumption. And so if we apply the simplifying assumption here, that is, we say the change is so small, it's negligible, then we're going to have just 0.100 on the top. X is going to stay the same, and then this 2.800 plus 2x is just going to be 2.800. And then we square that. Now how does the algebra look? Algebra looks easy, but we made these assumptions. These assumptions aren't necessarily true, are they? And we don't know. Okay, so what I say here is negligible for calculating x. For calculating x only. Calculating x only. For calculating equilibrium concentrations, must use x. And so it must use the x, we don't draw the x when we actually calculate the equilibrium concentration. So let's go ahead and calculate x here and see what that comes out to. And so I'm just going to take 0.1. 0.1 divided by 1.7 times 10 to the 7, 1.7 times 10 to the 7, divided by 2.8 squared. 2.8 squared equals. So I calculate an x of 4.7 times 10. Actually, let me get more digits here. I'm going to go 4.72411 times 10 to the negative 3, 6, 9, 10. Times 10 to the negative 10. Is that what you guys got? You got something different? Let me try it again. This messed up. 0.1 divided by 1.7 times 10 to the 7 divided by 2.8 squared. Oh, you're right. let me redo this. I must have miskeyed this. I got 7.503 times 10 to the 3, 6, 9, 10. Times 10 to the negative 10. Is that what you guys got? Yeah, okay. So out of a population of 0.100, how many made it back up the hill? So out of this population of 0.100, complex silver, how many made it back up the hill? Well, that would be X. And that X would be 7.5 times 10 to the minus 10. Is that very many? No, that's what you call kind of negligible, you know. Very few made it back up the hill in a large population. All right, so when we calculate X, we use a simplifying assumption here. But when we calculate the equilibrium concentration, we don't use the simplifying assumption. So going back over here, let's go ahead and calculate the equilibrium concentrations here. And that is the free silver ion concentration is just equivalent to X. So this will be 7.5. I'm going to carry extra digits to avoid round off error so it doesn't screw up my double check. 7.503 times 10 to the minus 10 molar. Okay, the ammonia concentration is going to be equal to 2.800 plus, I'm going to write this in decimal form. So writing this in decimal form, I'm going to need 9 zeros and then a 7 after the decimal place. Let's go ahead and do 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros and then a 7503. So let's add some zeros there. And so this is going to come out to 2.800. Then 6 more zeros. 1, 2, 3, 4, 5, 6, 7, 5, 3 more. Was that kind of a negligible change there? Yeah, that's pretty negligible.
When we're calculating X, are we using the same K value or the reciprocal?
No, the same K value. I didn't flip the equation. If I flip the equation, I do it. Instead, I don't have to flip the equation. What I'm doing is I'm just going to put all the atoms on the right side and then let it go backwards in this equation. I could have flipped the equation and then taken the reciprocal, and then we would be doing this, what we're doing right now, essentially. But that's not often done. When we do equilibrium calculations, we can go left or we can go right. It doesn't matter which way we go, you know. We'll reach the same equilibrium as long as we have the same number of atoms involved. The population of the atoms didn't change. Okay, let's calculate how much we lost. And so we started off with a population 0.100, complexed. So how much did we lose? So this is going to be 0.100 minus point. So I'll need 9 zeros. 3, 6, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 5, 0, 3. And so what is that? We'll punch that out in your calculator maybe, which I'll probably do rather than do this. Or maybe we'll do that. This is not too hard of a calculation. So this is going to be 0.09999992497. 2497.
For a second, you know how it's like plus 2x?
Oh, I just did plus X, right?
Yeah.
Oh, I screwed that up.
It's still not that big of a change.
Yeah, I'm sorry. We need to double this one here. So that's going to change this one to 15006. Is that right?
Yes.
Yeah, still, this is still a pretty negligible change. Even if we doubled the X, it still didn't change much. And let's say we round this to 3 decimal places. If we round this to 3 decimal places, what does it round to?
9.99.
Well, if we round this to 3 decimal places here, then we can drop this 9. If we drop the 9, we have to bump this one up. And so if you round this to 3 decimal places, it rounds to 0.100. Well, isn't that where we started? We started at 0.100, we end up at 0.100. And so it barely changed is the point that makes. But it barely, but I don't want to round it to 0.100 because if I round it to 0.100, like for example here, if I round this to 0.100, right? Then that's like nothing made it back up the hill, but something did make it back up the hill, you know, although it's tiny. All right, so these are the equilibrium concentrations. Now, how can I check to make sure the calculation is correct? Plug it back into the K equation, so let's do that. I'm going to do that before rounding these to the correct number of sig figs. And so that's going to be the complex concentration, which is 0.0. How many nines do we have? 8 nines. And so 0.0, 1, 2, 3, 4, 5, 6, 7, 8 nines. And then the 2497 divided by 7.503 times 10 to the minus 10 divided by 2.8. Then how many zeros do I have? 3, 6, 7 zeros. 15006. I think that's right. Square. Okay, can somebody calculate that and see what the K comes out to? Does somebody have it? 1.7000002.57. Done? 5 zeros? 5 zeros and then 257. Okay. Times 10 to the 7. Okay, so when we compare this to this, it's a pretty good match, right? Do you see that? Okay, I know it's a bit of a pain carrying all these digits, but if we round this, then it's going to throw the answer off a little bit, and then we start to worry, did we mess up the calculation, or is it due to round-off error? And so we don't want to be overzealous in rounding. But I think we went a little too crazy on rounding. We didn't have to maybe carry it that far. All right, so that means we're allowed 2 sig figs here. So this is going to come out to 7.5 times 10 to the minus 10 molar. Here we're allowed 3 decimal places. So this is going to come out to 2.800 molar. Correct number of sig figs. And over here we're allowed 3 decimal places. If we do 3 decimal places, this comes out to 0.100 molar. See that? There. All right, so that was a lot easier, correct? Are we out of time? All right, we're out of time, so. Actually, here, just try this one. You want to try something at home? Try this one. Fe3 plus 6Cn minus yields FeCN6 3 minus. Do 0.100 and 3.000 molar here, and then K is 1 times 10 to the 42. Give this one a try soon while this one's still fresh in your memory. The same initials, 0.100 and 3.000. Molar. Just try it. All right, so again, it's just this bottom one. Fe3 plus 6 cyanide yields this FeCN6 3 minus. K 1 times 10 to the 42. Fe3 plus 0.100 molar initial. CN minus 3.00 molar initial. Okay. So I'll see you tomorrow. Look for that link on Canvas. Thanks.